Hi everyone. In this lecture, we'll discuss the common drain amplifiers. So in common drain amplifier, you apply the input at the gate and the output is at the source. So one of the more we'll actually begin the lecture by discussing one of the more popular applications of common drain amplifiers, which is source transformation. Okay, as we will later see, the voltage gain of a common drain amplifier will not be much. In fact, it will never be greater than one. But still, why do we use this common drain amplifier in the first place? So first, take this case of a voltage source with a finite source resistance driving a load resistance RL. Okay, and we know from maximum power transfer theorem, the maximum power that a voltage source with a source resistance Rs can deliver is Vs square upon 4 Rs. And also, if you recall from the lecture on the passive circuits, we said that an ideal voltage source can deliver infinite power. So even if I keep making your load resistance arbitrarily small, the power delivered to the load resistance will keep on increasing. But by adding the source resistance Rs, we said that we can model the limited power delivering capability of a voltage source. Okay, a voltage source can only deliver a finite amount of power, and that can be modeled mathematically by adding a source resistance Rs. The maximum power that you can deliver to the load resistance is when RL equal to Rs, and that comes from the maximum power transfer theorem, and that value is Vs square upon 4 Rs. Okay, if Rs were absent, if there was no Rs, if there was no source resistance at all, then the power that you can deliver to the load resistance is Vs square by RL. This is the instantaneous power. What I'm talking about here, showing here is the instantaneous power. So Vs square upon RL. This is the power you can deliver. But because of the presence of Rs, the power is getting limited to, maximum power is getting limited to Vs squared by 4 Rs. And as you keep increasing the value of Rs, the power that's delivered to the load resistance also keeps decreasing. As you increase Rs, the maximum power transferred will hyperbolically reduce and eventually go to zero as Rs tends to infinity. So how do you fix this problem? The problem here is a voltage source wants to drive a load resistance, but a large source resistance is limiting the power that this voltage source Vs can deliver to the load resistance. So somehow if I can design a circuit which can deliver the same voltage Vs to the load resistance, okay, without much of a gain, you don't need gain, but you just have to deliver the same load resistance Vs to the no, to the load, I mean same voltage Vs to the load resistance. So first, what I've shown here in this figure here is that I have just introduced a common drain amplifier. Input is at the gate, output is at the source, so that I'm calling that as a common drain amplifier. In between the source and the load, by doing so, we'll see what happens to the gain. After once I place V0, we'll then see what is the voltage appearing across the load resistance. So to find the load resistance, what we will do is we'll try to simplify this problem. I have shown here, I have added the common drain amplifier after the source resistance. The load here appears at this point. To solve this circuit, what we can do is we can find previously the load resistance was directly seeing the source resistance with a source voltage with a finite source resistance. Okay. Now we'll try to see how will the load resistance see this modified circuit as a whole. So we'll try to find its Thevenin equivalent. Okay. So to find the Thevenin equivalent, you'll open circuit the load. When you open circuit the load, you should also understand that the input current drawn into the gate of the common drain amplifier is zero because you're looking into the gate, so the input current drawn is zero. So Rs, there is no effect of Rs. The voltage drop across Rs is zero. You're not drawing any power from the source. So that's what it means. So the voltage is going to be Vs here. That's the voltage that's going to be at the gate. And we are supposed to find the source voltage. Okay, I'm finding the open circuit Thevenin voltage across the load resistance RL. So first I'll assume lambda is 0, which means R0 is infinity. If you assume R0 is infinity, now when you're applying the input at the gate and output is at the source, now if you see, since your source terminal is open, no current can flow through this device. The drain current is 0. So which means GM VGS is 0. Okay. Since we have biased it with a finite current, of course, this device is being biased. So every device which has to operate as an amplifier has to be biased in the saturation region with a finite bias current. Your GM cannot be 0, which means the only variable is VGS has to be 0. If VGS is 0, it means that your gate potential is equal to the source potential. VG minus VS is 0 or VG equals VS. So therefore, it simply means your gate potential is Vi will be equal to V naught. So your source voltage V naught will directly follow the input voltage. So therefore, this architecture, this common drain amplifier is also called source follower. That's what I've written here. It's also called as the source follower. So the open circuit voltage we found out is Vi, which is in this case is Vs itself, the input voltage source Vs itself. So next thing we are supposed to find the Thevenin resistance. So we'll find the Thevenin resistance for the circuit. To find the Thevenin resistance, I'll have to short circuit the input and measure the resistance seen into the source terminal. Now here again we have made our assumption R naught is infinity. So since no current flow R naught is infinity, so I'm just directly looking into the source. Now assume now we can see that no current actually flows through the source resistance. So I can remove the source resistance. The voltage drop is going to be zero. So this you can directly write your output resistance R out is simply equal to 1 by Gm. Right? I mean you're applying a voltage Vx here. You can see Vx appears entirely across VGS, so there will be a current of Gm VGS flowing up to from source to drain because your VGS is negative. So the output resistance is 1 by Gm. So now the new Thevenin equivalent is shown here in this figure here. Okay. So the voltage is approximately the same, but now the source resistance is 1 by Gm. Now the load resistance RL sees this source with a transformed source impedance. So I can actually say this common drain amplifier, the insertion of the common drain amplifier has retained the voltage, of course, the voltage gain is 1, but it has transformed the source impedance. Now the load sees a different source impedance than what it saw earlier. Earlier, the load was directly seeing a source impedance of RS because you had connected it across VS. Now the load resistance sees a source impedance of 1 by Gm, and this 1 by Gm is under the control of a designer. Now Gm depends upon bias current, so therefore your output impedance is also a function of the bias current. Now the designer can choose the value of the load resistance 1 by Gm, the source resistance 1 by Gm, depending on the power that is required to be delivered to the load resistance. Okay, so this is one very important applications of a common drain configurations. It doesn't give you any voltage gain, but it transforms the impedance of the input source. Okay, so which means it takes a voltage at a different impedance and and actually it provides it to a load at a different impedance, at a lower impedance. Okay, so the now we will actually try to find the voltage gain. So this is Vs and the source resistance is 1 by Gm and the load resistance is RL. So the voltage gain, the voltage across RL is simply, you can easily show that it is GMRL by 1 plus GMRL or GMRL plus 1. So that's your voltage gain of a common drain configuration with a finite load resistance. Here I've assumed lambda is 0 or channel length modulation is 0 or there is R naught is infinity. Sorry. Okay. So I can choose GM to be much greater than 1 by RL, or then in that case GMRL is much greater than 1 and this result will be very close to 1. So you'll have the entire voltage Vs now appearing across RL. If I choose 1 by Gm to be much smaller than RL, the source resistance, the modified source resistance or the transformed source resistance to be much smaller than the load resistance, then you will have the voltage gain, the entire voltage Vs appearing across RL. So that's one main advantage of a common drain amplifier. So now again, like we did this analysis of common gate and common source, we will analyze everything like the intrinsic gain, the maximum possible gain, output and input resistances of a common drain configuration. So to find the intrinsic gain of a common drain configuration, what we can do is we have to assume R naught present. R naught is present in the circuit. So what we can do is in this circuit, I'll just probably show it here. So R naught actually appears between drain and source. So since drain is at ground, I can show R naught with respect to source and ground. It was actually between this, I can show it here. And your Vi is applied here and V naught is now taken across RS. Because drain is the common terminal, this ground and this is same because drain is at the AC grounds are same. Now I can treat R naught as a load resistance RL and simply directly write the gain as GMR naught by 1 plus GMR naught. I mean, I've just derived it for a finite load resistance RL, and we can apply a similar procedure. You can always find the equivalent circuit seen by R naught, and that's going to be VI. Voltage gain is going to be 1. So you will see VI with a source resistance of 1 by GM. So if you do a simple potential division of 1 by GM and R naught, you will get this expression. Okay, I'm just saying this pretty fast, but I think it by now you're comfortable enough to understand what I'm saying. So you will have VI is a Thevenin resistance, and 1 by GM is the as one Thevenin voltage, and 1 by GM is a Thevenin resistance. R naught is the load. So to find the voltage across R naught, it's going to be R naught by R naught plus 1 by GM. So that will be nothing but this result. Okay. Now the next important thing is the input impedance. Now, in case of a common source amplifier, we found that the input impedance was independent of what you connected the load, and it was always infinity. Okay. Similarly, in a common drain configuration as well, no matter what you do to the load resistance, the input current is going to be always zero. It might change the voltage gain, of course, but the input current drawn is always zero. So which means your Rn is always infinity. It is independent of the load resistance. Okay. But if you remember in common gate amplifier, we saw a very interesting relationship between Rn and RL. Okay. Now, similarly, the next thing that we need to find is the load output resistance in the presence of RS, finite source resistance. Again, to find the output resistance, we need to look. So you'll have a finite, you'll actually have R naught here. Now you're supposed to find the output resistance seen into the source. Again, since no gate current flows through this device, the gate current is zero, the current through RS will also be zero. So small signal current through RS will also be zero. So because of that, I can ignore the effect of RS, and the output resistance is simply going to be, there is an R naught which comes in parallel with 1 by GM. So it will be simply 1 by GM parallel R naught. Again, it is independent of RS. The same thing we saw in a common source amplifier, where we said that the output resistance was simply R naught, and it was independent of, I mean, common source amplifier without any source degeneration or anything. I mean, the simplest common source amplifier. And we said that the output resistance was R naught, and it was independent of the source resistance RS. Same way, in a common a common drain configuration as well, your output resistance is simply 1 by GM parallel R naught, and it is independent of RS. Okay, but in a common gate configuration, we saw a very strong dependence of output resistance on RS. Okay, so that's it about the intrinsic gain, and finally we'll find the loaded gain. So finally we have source and load, both of them present together, and see what happens to the overall gain. Now first, we are very quickly to we can eliminate the load source resistance because there is no current through the gate. So the voltage drop across the source is zero. So which means, what does it mean is the input is not drawing, amplifier is not drawing any power from the input at all. There is no current being drawn, means there is no power being drawn. The voltage source is finite, but the current drawn is zero. So the product of V into I is zero. So the amplifier is not drawing any power from the voltage source, but it is delivering finite power to the load. So actually the power gain is infinity for the circuit. Okay. So that's why even though the voltage gain is 1, we are still calling it as common drain amplifier. Okay, because there is a there is a power gain in the circuit, and as I said, for any amplifier, power gain, if it is greater than 1, then we know that it's an amplifier. Okay, so now to find the loaded gain, as I said, RS doesn't matter because the input current drawn is zero, so you can just directly short this. Now all you can do is you can simply find the Thevenin equivalent seen by RL now in the presence of R naught. Now once you have R naught, uh, the voltage gain will not be 1 anymore. It will be equal to intrinsic gain times Vs. That's what I've written here. And the output resistance is going to be R naught parallel 1 by Gm. So that's R naught by 1 plus Gm R naught. And that will be seen by your load resistance. So the expression for the gain can now be written in terms of RL R naught Gm. So this is your maximum gain. Rather, I shouldn't use the word intrinsic gain. This is your maximum gain. So I'll write the maximum gain is Gm R naught by 1 plus Gm R naught. We have used the word A naught to denote intrinsic gain, which is the product of Gm into R naught. So that you get it as A naught by 1 plus A naught. Okay, that's the expression for gain, maximum gain of a common drain configuration. Okay, and this is very close to 1, and this factor captures the finite source resistance. Your source resistance is finite, so therefore there is a slight reduction in the voltage across RL, okay, compared to the maximum gain, the unloaded gain of a common drain amplifier. Now, if I can approximate this R naught parallel 1 by Gm as 1 by Gm, okay, then I can rewrite the gain, the loaded gain as two terms. One, this is the intrinsic gain, Gm R naught by 1 plus Gm R naught. The other term is Gm RL by 1 plus Gm RL. So this term R naught by 1 plus Gm R naught is simply going to be this term. This term here is simply going to be RL by RL plus 1 by Gm. So from that I will get this term here. Okay, from this you will actually get the second term. Now if your GMRL, if you choose your GMRL to be much greater than 1, then the gain obviously will be very close to 1. Of course, we will be limited by the intrinsic, the unloaded gain, but it will be very, very close to 1. Okay, so that's it about common drain amplifiers. And here I've shown a very popular application of a common drain amplifier. It's sometimes, it is used as an amplifier mainly in the final stages when it's about to drive a load. And more popular application is a level shifter. So when you have two circuits with two different DC levels and you want your signal to travel there, of course you can always do a AC coupling and locally bias it or locally bias it. So for example, if you have two circuits, the quick way, the DC level here and DC level here are different. Then normally what we do is we just do an AC coupling and ensure that we bias it separately. Or the other way of biasing good can be use an amplifier, a common drain amplifier. In fact, you shouldn't call it. It's just a common drain amplifier. It's just used as a DC circuit here. There is no amplification. So it will actually shift the input DC level will be reduced by, I've written VTH here, which in fact it is VB minus VGS of this device. So the DC voltage at the output here will be VB is the DC voltage at the input minus VGS quiescent of this device. Okay, if you choose your current sufficiently large, then sorry, if your device size sufficiently large, then the VGS will be very close to VTH. So I've written, that's what I've written here. You can actually drop it by VT voltage. Okay, you can reduce the DC voltage of the input signal by VT by using an NMOS common drain amplifier. Common drain amplifier is a level shifter. Or you can use also a PMOS level shifter. Again, for a PMOS here, gate is the input, source is the output, so it's a common drain configuration. You can increase the DC level by VTH. I've written VTH here, essentially it is VGSQ. In this case, it will be VSGQ for a PMOS device. But if your device size is sufficiently large, very large, your VGS will be very close to VTH. So that's what I've written here. Okay, you can level shift the DC values of the input signal. Okay, so that's it about common drain amplifier. So very quickly, I'll just write the intrinsic, the unloaded gains alone for common drain, common source, common gate, and common drain. For common source, it is minus A naught, where A naught is GMR naught. I'm just using the word GMR naught, it's called intrinsic gain. Now for common source amplifier, A naught is the intrinsic gain. I'll write gain. And for common drain amplifier, it is 1 plus A naught. Sorry, this is common gate amplifier. And for a common drain amplifier, it is A naught by 1 plus A naught. Okay. And Rin of a common source amplifier is infinity. R out of a common source amplifier, for the simplest common source amplifier, is R naught. And for a common drain amplifier, again, Rin is infinity and R out is approximately 1 by Gm. It is actually 1 by Gm parallel R naught, but this is approximately equal to 1 by Gm. For a common gate amplifier, on the other hand, it is pretty complicated. It's not very, very trivial. Generally, the input resistance of a common gate amplifier is 1 by Gm. Output resistance depends on the source resistance. If your source resistance is very, very low, then it will be approximately R naught. Okay. Output resistance can be said very close to R naught if your source resistance is almost negligibly small. Otherwise, we know that we have seen the proper expressions for this. I'll just write those two expressions here. It's a strong function. Rn strongly depends upon what you connect at the load. So it is actually RL plus R naught by 1 plus GM R naught. We said it gets reduced. We'll see a reduced version of the load, and we saw how to derive that result. And the output resistance will actually be R naught plus RS. Actually, output resistance depends upon the input source resistance. Okay. So it is R naught plus RS into 1 plus GM R naught. So this is the overall expressions for input gain R in and R out of the three different configurations, or in MOS, especially MOS circuits, okay, in which a MOSFET can be used as an amplifier. The three different configurations in which a MOSFET can be used as an amplifier. Okay. So in the next lecture, I'll very quickly discuss about the common collector configuration, the BJT counterpart of a common drain configuration, and then probably we'll then move on to source degeneration.